The reactors used to, in the United States, had like 40–50% uptimes. I mean, they were horrible. And that was because of the parts thing. And when Exelon, they're known for going in, and with all the reactors, they went in and they standardized everything they could. You know, pumps, valves, motors. You know, the top heads. You know, the bolt. I mean, that's how crazily one-off these plants were. They would get like custom nut and bolts. You know, for like the pressure vessels. And so ComEd was like, no, everything's going to be standardized. And it took them like a decade, but now, like Byron nuclear power plant, which was one of the worst plants in the country for downtime, has had its like fourth refueling with like 99+% uptime.
Well, part of that is also due to 3 Mile Island, because after 3 Mile Island they realized that training was not good and was not uniform across the companies, and so they kind of forced all the companies and utilities to get together and agree to share their training and safety training and all that kind of stuff and procedures. So that at that time it was something like 65% was kind of the average uptime for, and it went up to 90, over a 90 after several years of this getting together, kumbaya kind of thing. We're all going to share our information about how to operate the plants, and WANO was part of the system that got that going. Made a huge difference.
Yeah, that's 3 Mile Island. What an indictment of how poorly managed the industry was back then.
Yeah, I have a book somewhere that I got from a guy that was written by the training manager at 3 Mile Island afterward. And basically,
I don't know if you should be the one who writes.
I know, that was kind of interesting, but it goes through all the things that happened that were wrong, you know. And like they had an inspection sticker on like a twist tie hanging over a gauge that they should have been able to read.
Oh, nice.
They would have told them what one of the things that was wrong. So how did you actually get involved with all this in relation to like Kirk's timing?
In 2005, I run an engineering company in product development, materials development stuff, and so we had a client back then who was I can never remember what the hell he was using. Oh God, it's they use it in flat screen TVs quite a bit.
Oh, you mean like LCD stuff?
Yeah.
Or a material?
Yeah. Well, anyways, it'll come to me. I look at a periodic table. I could pick it out.
Oh, okay.
It's the Something Corporation of America has a monopoly on it, and it's based in Chicago. Anyways, there's like he's like, John, find out where I could buy like 1,000 pounds of this stuff. Yeah, so he had his own stockpile, and so I called up the Indium. I called up the Indium Corporation of America in Chicago. And I'm like, hey, what would happen if I could stockpile 1,000 pounds of Indium? And he goes, we would kill you. And I'm like, what? And the guy was not like, haha, you know. He's like, if you try to start hoarding this stuff, because it turns out there's never more than like a 2-week supply ever in the United States. It's incredibly rare. The price was skyrocketing. So my client said, well, what else can we use? You know, and he was basically running through the periodic table, and we got to thorium. You know, and just like every other thing we'd done, you know, he's like, tell me what it is, you know, tell me about it, you know, maybe. So I, thorium, Google, you know, and I'm like, wow, that's an interesting. And Kirk had just literally probably like a month before started his little energy from thorium site. And so if you look, I'm still like member number 7 or something like that. I'm like, hey, can you tell me a little bit about this thorium? I got a client, you know, and and then of course I found other stuff like Bruce Hoagland's stuff, and then I found out that they did do some really interesting metallurgical stuff with it, you know. So I was like, when I reported back to the guy, I was like, well, you know, it does have interesting uses. It can't help you. He's like, and I'm like, you know, but something interesting. It could save the world. And he's like, really? He's like, can we buy, you know, can we stockpile it? I'm like, oh no, that's like garbage, man. And he's like, what the hell what do you mean? And I'm like, you know, if anything, if you could figure out a way to stockpile it, you know, you could make a lot of money because people would pay you to take it. And he's like, all right, well, on to the next thing. So he moved on to the, you know, the next element that he wanted to look at, but I just never sort of let it go. So I was just like, it was just stuck in my head. I'm like, boy, that's a real good opportunity there. I'd always had a soft place in my heart for nuclear power. So I remember back in the 80s watching like NOVA programs about nuclear reactors that could shut themselves down and stuff, and I must have been seeing stuff about IFR or EBR1 or EBR2 or some pebble bed reactor, you know.
America has roads that could use roads and bridges that could use some updating, right? So looking at a big problem,
4,000 of them.
So looking at a problem like R&D for thorium and the molten salt reactors, like how can you sell anyone on spending millions and millions of dollars on research for that when even just getting roads fixed is such a no-brainer?
That's not how you do it, though. I mean, that's, you know, then I mean, that's the argument people make for, like, there's a starving child somewhere in Appalachia. Why are we sending men into space? You know, it's like you would be shutting down every extraneous program up until the point that nobody ever skinned their knee or shed a tear. You know, I mean, if you know, you have priorities, and it's like you have to do all this stuff at once, and you're not gonna completely solve any one problem.
Right, and the starving kid's not going to get medical attention or food if the bridges don't carry the food across the rivers, you know, and things like that.
Well, do you have any like liberal friends where it's like nuclear power is sort of one of those things that not a lot of people are focused on, right? So it's like there's something like Occupy movement and stuff like that, where it's like it gets probably millions of people are at least somewhat aware of the Occupy movement. How do you place this in the context of, well, maybe you should spend more time on science and technical issues than like social movements and stuff like that? Like, do you ever have to try to explain to people the basics of why nuclear power is actually worth thinking about or spending time on?
Jim Kennedy and I, our personal particular focus, where we thought we could have the greatest, you know, impact, was to spend time with, you know, what you would euphemistically call decision makers, you know, but I still do try and do outreach to the general public as far as that goes, and so I gave it, you know, I think what happens is when you give a talk to like a local Sierra Club, or there's a thing out here called the College of Complexes, which is sort of a very liberal, I guess you could call it, the learning group, sort of an independent learning group, and I find that when you're able to have a decent discussion, these people are generally open to it, and once you educate them, they buy into it. The hardest part is that middle thing, the organizations. When you try and talk to NEI, Nuclear Energy Institute, or ACS, or Union of Concerned Scientists, those people, you know, their members might like what you're saying, but the management, their jobs depend on you know, funding their core message, and so, you know, if you could get NRDC to openly support nuclear energy or something, I mean, you have the most experience, you know, with.
Well, it's interesting because the NRDC guy was there at the Blue Ribbon Commission when we were there in DC over a year ago.
Here it is.
Here it is. That's fast. And he was not at all interested in nuclear power.
I don't think they want to drive it along.
Oh, we're stopping.
We're here.
Not on purpose. He didn't see the entrance coming.
Oh, we missed the entrance.
So, how did the conversation go then? Like, how does an actual specific conversation go with
the conversation starts with, would you like to have a discussion or presentation on alternative nuclear power or safer nuclear power or whatever? And certain groups like the NRDC is just kind of blindly anti-nuclear. So it's very odd because they're not interested in changing the policy. So, for instance, John Scott and I, as Sierra Club members, are trying to get the club to just evaluate and reevaluate their existing nuclear policy, which was changed from pro-nuclear to anti-nuclear in 1986 after Chernobyl. So that's very hard because there are entrenched interests at the management level of these organizations, like the board of directors and so forth, that don't want to jeopardize the membership participation based on changes in policy. So if they admit that they made a mistake in 1986 in going anti-nuclear, and the membership sees this, they kind of risk their own continuing as directors and whatever. It's political. It's a bureaucratic situation. And
when you're talking to an individual in a bureaucratic position about this, do they just not read the
well, some of them are. Okay, so here's what happens. So at the middle level, where you have heads of task forces or like committees, those people will say, well, I'm always anti-nuclear. Or they'll say, well, no, I can support nuclear, but I can't say that because of the politics from me up in the organization.
But politics are also money.
Yeah.
You know, these guys make their living. So that the average member has a job and pays his dues, but the guys up at the top. And when you look into some of the funding of some of these groups, mysteriously, you know, you've got the charitable arm, you know, of the coal companies and oil companies and natural gas companies, you know, and they have a vested interest in keeping each other and nuclear, you know, on the ropes. I mean, you saw that in the movie the other night where the oil company wants you to go solar because they know solar is never ever going to be a threat.
It's good to be here. I had the opportunity to come. I jumped on it. Argonne is steeped in the nuclear history. Dates back to work with the Manhattan Project, and then of course the first nuclear reactor, the Chicago, gloriously named Chicago Pile, designed by Enrico Fermi, and they set it off under a sports stadium in Chicago. Their safety mechanism was a couple of guys, I understand, were standing by with an axe in case things went wrong, and so you have to start somewhere, and we've come a long way, and we have a long way still to go, and a bit of a transformation to make onto different reactor types where axes won't be necessary, and the fuel will flow in liquid molten salt. And anyway, it started here, and good place to come to see where it might be heading is to go back to see where it started.
My name's Roger Tilbrook. I am probably the only person in the DOE system with curator on my business card. I can't guarantee that, but I think that's pretty close to the truth.
I want to be sure that I can hear as much about Rick Rover as possible, because my understanding was that he had a very aggressive timeline for nuclear-powered subs, and even the first power reactor, it's like he was told it would take forever, and he pushed it through very quickly.
Absolutely. He's an absolute termagant and drove the program, and some of the other managers at DOE, this is my quote, who have been less successful than they should have been, were because they thought they were Rickover, and they weren't. So that's he pushed this thing like crazy, and on very aggressive timelines. He insisted on everyone being trained, everyone being up to quality, and no excuses. You know, you did it right, and you did it right the first time. Now, what he did towards the end of life of the shipping port, he wanted to prove he could make a light water breeder as opposed to a fast reactor breeder. So he did it, and he put thorium in it. The only problem is the core turned into a gigantic, humongous Swiss watch that had to be that accurate with a million little springs holding it all together. I think they actually got criticality, but their breeding level was very, very low. It's about 1.01 or 1.001. It wasn't creating well, all these reactors in the submarines are basically almost 100% 235, about 92% 235, so it's high enriched. It's bomb grade stuff. So that's what they'd originally have in shipping port. So when they started taking out some of the U-238 and replacing with thorium to see if it was going to work, it made it very complicated and very difficult to work.
Why was it that much more complicated?
I think it's because he was trying to shoehorn a different nuclear physics into an existing system. No, he's trying to do it in a small size system. It's perhaps 60 megawatts electric. All the geometry is defined, the core barrel is there, the core plate is there, so you've got all the sizes, all the dimensions predetermined for you.
He didn't have very much money to do it either, I understand. Radkowski was his physicist
I have no idea who
and he,
was doing
yeah, I read in Rick Over's,
memoir.
well, it was, I think it was in Weinberg's too, that they had so little money because the people in charge now of the AEC were not interested in the breeding. And so he kind of snuck Radkowski in there to put the thorium in.
He did that under the naval reactor program.
Right.
We used to have a separate naval reactors division here in this lab, working just on naval reactors and naval programs. So rather than all the other research stuff.
And I think they came out with 1.2% more fissile in 1982 from 1977 when he started doing that. Right?
It was really small. It's peanuts.
But that's okay. It was more than one.
It's more than zero.
That's the full-size mock-up?
That's a full-size mock-up.
That's a full size, and that was producing how much?
About a megawatt.
A megawatt.
And is this were these metallic fuel rods that?
It's metallic, mainly 235. I presume it's probably in steel.
Oh, this was like, and it didn't have water flowing through them, just air.
No.
Sodium?
It's got NAC in it. NAC is
NAC, yes,
sodium, potassium, eutectic. There's liquid at room temp, and they pumped it downwards instead of upwards.
Aren't the neutronics of potassium inferior to those of sodium though?
They wanted something that wouldn't freeze,
and that's easier than sodium.
And so you needed NAC. Potassium doesn't do it, sodium doesn't do it, but NAC has a eutectic point.
Minus 11 C or something like that.
Yeah.
So when they say it's a sodium cooled reactor, it's actually a NAC cooled reactor.
Well, no.
They never said that this one's a sodium cooled reactor.
This was the first one.
They've always said it's a NAC cooled reactor.
Yeah, NAK.
Okay.
Sodium, potassium, eutectic.
All right.
It's just horribly oxidizing.
Well,
It's more reactive than sodium.
it's much more reactive than
Potassium
sodium.
is easier.
No, we used to do this in school, put potassium in water, and you get a beautiful purple flame.
And the NAC
Yes.
is nastier in water because it's
NAC is even nastier. Yeah, it's far more
It
nastier.
emulsifies in the water.
Yeah.
yeah.
Now this next one over here is experimental breeder reactor number 2. It put together, went on power around about 65, 67 time zone, time range. It's 62 megawatts thermal and 15 megawatts electric that went into the power grid.
So about 25% efficiency.
Yeah, something like that.
Okay. And then,
This is the core.
those pins over there?
Yep, we can.
Okay.
Yep, those pins over there.
Okay.
Sodium cooled upward. When you wanted to refuel it, you could take it out here and put it over in the fuel basket and then put in fresh fuel that's now up to temperature back in the core. Then you can go back to power, and then you can transfer the fuel out of the fuel basket and take it out while the reactor's at power and save time, so you improve capacity factor.
Okay, and then this is called the shield cooling duct. And I'm just wondering, that right there, it looks like, this right here, the blue, it looks like air ducting.
Yeah, that's air ducting.
Okay,
that's air ducting that goes in and goes up the outside here, so the tank gets some cooling into the radiation shielding that you got around there.
Okay, great. And then this thing right here, I want to drill in a couple questions on this, if I may.
Okay.
The loss of flow test and the loss of heat sink test. Where's the heat sink? Loss of heat sink test, it says simulated a complete blackout, so the power was lost to all cooling systems. So your cooling system would be where?
Well, you've got primary sodium in here.
Okay.
Then the secondary sodium comes out and goes to a steam generator. Now, I'm not sure where the steam generator, I think the steam generator is actually in a separate building over here with the turbine.
So you have two complete separate batches of sodium?
You have for fast reactors, for sodium reactors, you've always got two separate loops.
Okay.
The primary, which may get gets radioactive.
Oh, your clean sodium and your dirty sodium.
Yeah.
Okay, I
So
got
then
you.
it's the clean sodium that goes to the steam generator.
Okay.
And then that generates the steam that goes to the turbine. So if you get a failure in the steam generator wall, you haven't got radioactive sodium.
I got that. Yeah. So this thing here, this loss of heat sink test would be turning off the power to the secondary, so you're not drawing the heat out of the core. Is that what the heat is changing?
You would shut down the tertiary, the water system.
The tertiary, okay. And so this other one, loss of flow test, is that shutting down the intermediate?
The loss of flow test is shutting off the pump. It's turning off the primary pump.
The pump for the primary sodium.
Yeah, it turns off the pump that's somewhere in.
So these two tests are turning off the primary and turning off the tertiary.
Yeah.
Okay. But at all times, the core was still bathed in sodium.
The sodium's there the whole time.
Okay.
The only thing you're doing is you're also doing it without scram.
Right, without control rods going in.
Without control rods going in, so this gets so warm, the fuel assemblies expand, the outside,
the pins lengthen?
The pins lengthen, they expand sideways, pressurizing up against the core, the core rigidity structure. As it goes round, you get hot sodium coming in the bottom, so the bottom plate expands, and that opens up the core so much that that the nuclear characteristics.
Does it actually separate the pins one from the other?
Yes, they'll expand as well.
No, I mean the pin assemblies, are they like separated one from the other, or are the pins within the assembly getting fat, or both?
Everything.
Okay.
Everything that can expand expands.
Okay, great.
So it's the fuel expands, the clad expands, the
whole damn thing expands.
The fuel assemblies expand, the core support structure expands, the core plate underneath expands.
Gotcha.
The control rods lines up here.
No,
the control rod.
That's the constant.
The control rod lines here expand, so that moves the control rods relative to some datum point.
Okay, so the one last question that I have was that once they shrink back down, can they go right back into service, or do you have to put in fresh ones?
Well, when it starts cooling down, it'll contract again. And then it'll heat up.
Right.
So it can pulse. So when you look at the thing over here, the trouble is these tests were done about 2 weeks before Chernobyl.
Yes, that's right. That was
so
amazing.
no one even knew about this, which is a shame.
Yeah.
Bob.
So my question was, this was not commercialized, right?
We were going to. It was called Clinch River. I was working on Clinch River. And then Al Gore, who thought that plutonium is nasty, wicked, and evil, and we shouldn't have anything to do with it, persuaded Clinton to shut the program down.
Yeah.
Clinch River, this
Well-
was Idaho, wasn't it?
No, Tennessee. Remember, that's the place in the movie.
Clinch River was in
Oh, yeah,
Tennessee.
okay.
Yeah.
One,
Tennessee?
right.
Got chain link.
But,
Yeah.
but this
Yeah,
is but this was all at Idaho.
Oh, this wasn't it?
Yeah,
This
this
is
was not in
This
Idaho.
one's at Idaho.
So when the emergency's over, you can keep the same pins in and go right back to business?
If something like that happens, you're going to take everything out.
I would think.
You're going to take the thing apart.
I would think so. I just wanted to check on that. But
So Mike,
I take it
before you
yes.
go, this is what we depend upon in the this is at the molecular level in the salt reactor because it expands. The salt
Exactly. That's
expands.
why I wanted to get
So it's the same thing,
wanted
except
to
this
drill
is done
down
at the
into the
physical
expression.
level, and so with the salt, it's easier to
Right.
have this
Yeah,
happen.
that's why I wanted to drill down and get some questions answered. But great, that was very informative. Thank you, sir.
So are we on sodium now as opposed to NAC?
This is sodium.
This is sodium. And I missed in the beginning, is that storage bin, are those rods getting ready to go out, to go in or out?
Both. You put, there's a certain number of holes here. You'll take out the used fuel, put new ones in, knowing where they are.
Right.
So they're up to temperature and what we call thermally conditioned before you take them there and put them in the reactor.
I'm not understanding the context of that Detroit reactor that had a problem. Like, well, how is that different from here? Is this a different type of reactor entirely?
That was the first experimental breeder, or not first, but they.
The initial Fermi fast breeder reactor was built by Detroit Edison. They wanted to try and do something, but not quite ready for prime time. It was made with metallic fuel like this. Actually, it went online about the same time as this one. And it was, they wanted to get experience in a commercial environment. We had some Japanese people supporting us. There's PDCA and APD, two different organizations. One was doing the design and of the plant and the analysis, and the other one was more focused on the construction and operation.
Really communicating together.
And the problem is, the AEC said, well, what happens if you get a meltdown? So they said, okay, we'll put some zirconium plates underneath. The trouble is, when they put them in, they only tack welded them, and the vibration of the sodium on them tore one of them off, or one or two of them off, the sort of saucer shape they had underneath, and went up and flattened underneath 2 and 2.5 assemblies, and basically melted it down.
Blocked off the sodium.
Blocked off the sodium. So there's a significant meltdown, but it was interesting. They cleaned it all up, and actually they had a meltdown in EBR1.
Yes.
But they cleaned it all up out there in Detroit, and the only reason it didn't go back to power was Milt Shaw was insisting on oxide fuel for FFTF and Clinch River, and wouldn't help give them some money to buy another core load. For want of a couple of $1 million, the plant went down. Now here on EBR1, these things expanded and contracted as well. And they got to the point, it's one of the first times when you got some control theory GS analysis of things growing and contracting. So it would grow and go and lose power, then it would cool back down and go back, and eventually a couple of the pins touched and they melted. So they cleaned it up and they were back to power again in about 6 months.
But the problems with the two reactors before, like when you guys talk about passive cooling in this reactor, I just want to know if that's not what's addressing the problem with the previous reactors. I mean, the one where the thing came loose because of like that's just the fact
That is a totally. You don't design reactors like that anymore.
Okay.
It's like saying Chernobyl can't happen here because we don't design reactors of that type, and that's true. We don't go around. I've actually got 2 or 3 patents on core catchers, but they aren't just add-on at the end. They're designed in as part of the plant, or catchers, some cooling catchers underneath the reactor. So those are ones I did for FFTF and Clinch River.
So by the time we get to EBR2, we have the word integral attached to fast reactor. What's the integral mean?
Well, it's because we got the reprocessing part of it over here. They wanted to do Clinch River with oxide fuel. What they did here is they're taking all the experience we had out of EBR2 with nettle fuel, and by the time we finished, we understood the way nettle fuel functioned and operated. Designing the reactor to be passively safe, but then you take the fuel, you chop it up, you process it electrochemically, and then you come out with your uranium plutonium mixture to go in the next plant.
So EBR1 did not have the reprocessing.
Yeah, the EBR1 did, but it was a different type of reprocessing.
All
That was all just melting. You just melted it down, skimmed off the slag off the top, which had this samarium in it and stuff like that, and then you just went through and did the next, put a bit more enriched uranium in it to see it through, and kicked it back in again. The new, this one, you're taking a lot more out because you're doing it electrochemically.
So is this more like what the French do, the electrochemical processing?
No, they use aqueous processing.
Acid.
But which one they're using, I don't know offhand.
What did they do with the Krypton 85 and the Xenon 135 that came out?
You take it away and bottle it and compress it. Compress it and bottle it.
And they just save it until it decays, or
ship it off and let it decay.
yeah.
So ship it off and
Ship it off and let it decay.
Okay.
So somewhere there's a big room full of gas bottles. Yes.
What happens if there's a leak?
Don't like it.
Sodium reacts with the air and the water.
All this area here, if you get a leak in here, in general, you try to have everything inerted. So you haven't got air typically right next door to your sodium surfaces. It's inerted, so you can spot the leak first. If you just get a small leak, you can handle it with freeze packs, if you like, to go with it. But everything isn't going to come right out. It doesn't. You're not getting stuff from the core getting out into the air. People normally can't walk around the surface of this because, I'd say, in a normal fast reactor it would be inerted, but there are areas that aren't. You can either go in suits, or you've got significant areas on the secondary side and all the tertiary side where the steam water is, where everyone can go in normal processes. And it just depends on the philosophy of the plant. If you may allow air much closer to the actual reactor in some areas than others. If I've just got a little tiny thin pipe that can't let very much flow out, you'll have a different access availability than a big sodium pipe that's 2 feet in diameter with several hundred pounds per hour flowing through it. So it's all a matter of graded safety depending upon what the circumstances are on the part of the plant you're dealing with.
Can I ask, is it easier to build the piping for this to pipe sodium around? And it's not under pressure, right? It's atmospheric pressure.
It's atmospheric, basically.
Is that easier than building the piping for pressurized water reactors?
Oh yeah, pressurized water reactor has to take 2,000 psi, which is a really thick pipe. It's typically 4 to 8 inches depending on the diameter of the pipe. Yeah, the big problem with designing and building piping, that is to make sure you don't have any flaws in it and everything flows right, and all the welds are correct. Whereas here, it's relatively thin pipe. The maximum thickness is perhaps an inch or an inch and a half. So you just take it and you bend it, and then weld the seams. So it's a much simpler process. When they decided that it was probably easier to build a piping system than it was to build, because they're relatively small, than build great big 30-foot steel tanks with the stuff inside it. And it's more accessible because the core is closer to the edge. Because the reactor vessel is perhaps here instead of all the way over here. So it's quite a different proposition for getting at things.
Can you talk about Yucca Mountain? The fact that you said they were going to put the whole fuel assembly in there, not do the process where you separate?
That's what they were planning on doing.
Yeah, in fact, there's a Sandia researcher who just showed up at Stanford a few months back who was explaining how they were going to do boreholes where they could drop the whole fuel assembly 5 kilometers down in a borehole. Wow. Talk about wasting valuable stuff.
To me, all you're doing is creating a plutonium mine.
Right.
It just makes it more complicated getting it out and using it when we're going to use it in 15, 20, 100 years' time, because we will. We need it.
Right. It's a resource.
It's a resource, absolutely. Yeah.
Do you see a prevailing opinion here about molten salt reactors? Do you have a prevailing opinion about molten salt reactors?
We haven't been funded to look at molten salt reactors.
Okay.
All the funding, we're on this what's it, G4, whatever they're calling it. Anyway, we aren't getting any money to work on molten salt.
But there's no opinions about
the opinion is simple. Build IFR. That's it.
Okay, that's the opinion. Okay.
The problem with the MSBRs is that they've never done it. They had one at Oak Ridge for a little while that worked with high enrichment uranium. Then they went through and did a couple of little tests. One, they threw in a little bit of plutonium to see how that would work with it. And then they did another test a little while later and threw in a little bit of thorium, just some materials compatibility more than anything else.
Well, they did,
but they've never done it.
Also.
Well, 233 is what comes out when they put the thorium in.
Yeah,
but there wasn't very much, and it wasn't for very long. I've got a report on it, and it was just one little run in the few runs, and they only ran for about 3 years. So they didn't.
They ran from 65 to 69 for 17,000 hours, 17,500 hours. That's quite a bit.
Well,
when it's experimental reactor.
Okay, are we heading for the bus now?
Everyone's like, these are so great and they don't melt down. It's like, all right, you want me to play devil's advocate? There's some real issues with trying to get the commercialize an MSR, and the two biggest are gas handling and remote maintenance. And it doesn't matter how good you design something. No, because there's only a small chance that the salt that'll be used needs lithium. I mean, I will curse you and make you go start talking to Boyd and Kim Lawrence Johnson to give you the dissertation on salt, and then we'll see you next week. But yeah. So, and even like Dave LeBlanc, there's at least 15 different types of salt that he's considering. The hot cell, they don't call it a hot cell for nothing. Right. And even if you design it and you did a great, you got a diesel engine Rolls Royce of a thing, over the course of X amount of years, you got to get in there. Nothing lasts forever, and humans can't get in there.
If you get radium,
do you know the kind of science, the kind of experimentation we could do?
Radioactive TC in your body, it pees out as pertechnate anion,
TCO4 minus,
and it goes right to your kidneys and never rests. It never stays in your bones or anything.
Yep. It's totally soluble.
So weak, they allow people to pee it out, and they just say double flush the toilet.
Right.
You don't even need to double flush the toilet. You can just.
You ever see the geometry of that? I love that thing. The TCO4, the pertechnate.
Tetrahedral.
It's tetrahedral.
Permanganate, but stable.
Yeah. Yeah.
It's a non-oxidizing form of permanganate.
God, and you can make, God, there's so much cool stuff you can do with that.
And when you add 200 ppm technetium to low carbon steel, it has the performance of stainless at no additional cost.
Well, but there's a perfect example of making a super strong alloy cheap. It's very low. It's what, 250,000 year half-life?
The half-life is 250,000 years.
Yeah.
It's only giving off weak beta.
Yeah. So and it's a weak beta emitter anyway.
It's 9 or 10% of the fission yield.
Right.
Moly 99 and technetium 99 dominate, and you have to get them out. And if some of the uranium is just slightly penta, it bubbles out as hexa moly and hexa tech.
Right. Hexamoly. Yeah, because hexamoly is 35 Celsius is the boiling point. The melting point is, or the melting point is 35.
It's a very narrow. It's a very narrow, super narrow liquid range.
It's like 35 Celsius is the melting point, and the boiling point is like 40.4 Celsius.
And if only a few percent of the uranium is +5, then you'll get a mixture of penta and hexavalent fission products, and that makes a bigger liquid range.
Yes.
And that would be more easy for us to handle because then they're less volatile.
Yes.
You got to understand the only reason any of these things exist, clean coal, solar, wind, they're not for energy, they're for jobs, okay? They're all going to create thousands and thousands and thousands of jobs.
Destroy jobs by sucking the tax that way.
Just saying, what they hear is, hey, you're going to need something that's going to need constant maintenance and constant surveillance, and you're going to need to really...
Constant pauperization.
Yeah, and their thought is, hey, if these things make just enough power to like break even or something even remotely close to breaking even, then they can justify the fact that they broke even, but they also took 3,000 people off the welfare rolls.
Right. Well, the big thing is and I have to deal with this with the people in the Sierra Club too, is to identify the actual things that are valuable and what are the things that are, as you say, subsidized beyond reason, right? And don't really work.
Right.
So the local solar stuff is great because you can install it locally. You don't have any land. You don't have any power loss from some distant farm. All that kind of stuff. That's great. But again, it's variable. So you have to have some storage of some sort or some throttleable backup.
Better than storage is just flexible MSR capacity.
Yeah, well, if you want to do it that way. Well, but there will be storage because it has to be for EVs. EVs have to have light, efficient, high power density storage, and they will. So we will have that.
But with lithium or lead acid?
I don't know what. Ultra capacitors, to me, as an electrical engineer, is the ideal thing because if you do nanotechnology and get capacitor elements that are nanoscale, and you can, this is made out of very light material, doesn't weigh anything, and it's got high power density, you're great. So I think that probably would be one of the best things, and it's non-polluting because it's not made of anything but carbon.
You really think there will ever be economic utility scale battery storage or energy?
I think there will, but the thing that's going on...
like pumping up a hydroelectric dam or something?
Well, the thing is that there are so many different ways to approach it. There are passive ways, there are ways in chemistry, there are hydraulic ways. So again, you got to figure, you can't tell which one's going to be the right one. It's just like, right?
Well, it's like, I mean, it's sort of clever that they use the solar concentrators are basically using fly neck, and they're melting the salt, and they pray to God that it stays molten overnight while it runs the turbines. And
well, in California, at least one of our concentrating plants in the desert has a gas line to it, so they can keep it running at night.
Oh yeah.
But that's cheating.
Well, it's making money. The whole purpose, come on, you know this. The whole purpose of this is for the investors and the guys behind it to make money. So we have this crazy solar plant that burns gas, wastes 10% of its electricity in long transmission lines, right?
Sure.
So I mean, the whole idea of the farm, whether it's a wind farm or a solar farm or an Oreo cookie farm, is crazy because you waste all this stuff.
The story of what it was like to get a new trunk line to San Francisco. Wired magazine. They're like, here's where the the interconnect would be. Here's SanFransisco, and they're like, we're not running a high power line through my neighborhood. I'll get electromagnetic radiation. So then they went south, and finally they did this. They went the opposite way, up over the mountains, out into the ocean, down the ocean, underneath the Golden Gate Bridge, and they're like, is that far enough away from people? And even then, I mean, it's like 6 times longer, and like you say, like 10% more transmission loss, and having to put it underwater, an underwater cable, the expense. So it's like the insanity of the NIMBY thing is just like, can't people give? I mean, why can't they defeat that with some sort of educational campaign?
There's not enough of that going on, and the media is the prime source of the ability of these groups to mislead people, right? So like the anti-nuclear folks can mislead everybody because the media will publish everything that is bad about a nuclear event. But
why is there no educational campaign by the nuclear industry that, it seems like the nuclear industry is ineffective in moving public opinion on this. What is about that industry?
There's no real nuclear industry. There's a coal industry, but there's no nuclear industry.
There's no unified nuclear industry, and there's what little education, like ANS has a student education initiative, which is, on its face, it's okay, and the actual programs are kind of nice, but like, how many students ever get exposed to it,
I never heard of it until recently.
Yeah, a couple thousand, maybe 100 teachers get educated in it, and so that's a whole 2 teachers per state, It's like the efforts to educate the public. I'm pretty sure the nuclear industry wishes it could just hide and hope nobody notices it, and it could just go about its business without anybody paying attention. And
you should find out what the French have done, because the French made a point of educating the average Frenchman about the benefits and safety of nuclear power in France.
Same thing with the Japanese, except the Japanese didn't follow it up with actually running safe reactors.
Well, TEPCO didn't.
Well, you remember the near calamity that was, to nerds, would be fairly widely reported like a decade ago, when they were like, the story was some Japanese guy who was on his way to lunch at the reactor, and he's like, oh, what hit my head? And he looks up, and there's a little puff of steam coming out of one of their big high pressure lines, and some of the condensate was. He's like, and I don't even know if they scrammed it. They're like, oh, no, don't worry about it. But finally they sort of relented, and they shut it down. And these original, they magnetometer, they magnafluxed it, so they sucked it and put it, and these high pressure steam lines that started out like 2.5 inches thick were now like 3/8 of an inch thick. The steam's super corrosive, and the I think the American consultants were like, when was the last time you changed out these pipes? And they're like, never. They're like, what? You can't, So so it's that sort of thing where it's like defrayed, maintenance.
Well, but the French did it right, at least, because we know they decided on a standardized reactor to use and mass produce them and install them and upgrade them as the design as necessary. But they educated the average French person, which was.
I'm not aware what public opinion in France is about nuclear power, but I hear about France walking away from nuclear power. How is that even possible? I mean, that is the nuclear. If there's any nuclear industry, there must be one in France. How can they let that even be a question?
France is practically nationalized. I mean, Areva is a national company, and they have I believe 3 standardized designs. They build all their nuclear plants in a factory, so they're not like us where we one-off build our plants. AP1000 was supposed to, we'll see if they ever build more than 2, then we'll know that but that's supposed to be a standardized plant. And it's got good numbers when you look at it. It's like, they use they use like something like 7,000 less miles of wire, you know, 3 fewer pumps, 10,000 fewer valves. I mean, it's like everything was to simplify, make it robust through simplicity, you know, and they, I mean, it's better. I mean, if you want a light water reactor, that's what we should have been building 40 years ago. But the fact that it took them 22, 23 years to get through NRC approval for what basically is just a good old design is insane. It's insane.
I would really like to see somebody, you know, I can send you the name of a woman who's in charge of the nuclear engineering now at UC Berkeley. Buchik. She's from Eastern Europe originally, but she knows all about the French system and what they've done over the years. And it would really be good to have some sort of little documentary about, well, here's what an average Frenchman thinks about nuclear power, and this is why.
Well, and here's the thing, unlike, like you saw in that movie Pandora's Promise, and Susie Hobbs's Pop Atomics, she took a nuclear tour of Europe, and you can go to Areva. You should do that, Gordon. You know, use some of your precious funds, and you could go do what they did. There's one room in one building that stores all the nuclear waste that France has ever generated, and you can go in there, and you're not going to be baked alive. You won't have increased incidence of cancer and a reduced life expectancy, and yet you're standing on top of thousands of tons of spent nuclear fuel. And the other thing that France did, I don't know if it helped with public opinion much, but it was very brave of France and quite an engineering feat for a company that makes, you know, the Le Car to go and believe in their engineering enough that they built a uranium reprocessing facility. So when they spend their fuel rods, they actually run it through and they reprocess their fuel. I think they get like 3 bites at the apple. So that, you know, they're getting like 15 to 20% of the energy out of their fuel rods, where we're getting like 1, 2, 3%.
It's just really professional. I mean, it's a uniform, regulated,
very good
professional system, and the storage facility for the fission products really is the dominant content. Is public. It's open to the public.
It makes a vinegar molecule. It makes like.
It's open to the public, so they can go and see where the fission products that can't be used are going.
What do you think the world would look like 50 years from now if we continue on the path we're on right now?
Oh, it'll be a freaking mess. Look at Venus. Look at the planet Venus. The planet Venus is a really good example of runaway greenhouse effect. Just look at the atmospheric chemistry of Venus, and it'll tell you, don't do that. So let's just look. It's very simple. Let the scientists do what scientists love to do. We, people like me who are very interested in energy and who are chemists and physicists and whatnot, chemists like me, we want a mature, intelligent, robust energy landscape. Will that involve nuclear? I sure hope so. Will it involve fossil? Yeah, it kind of has to. Because just like a stock portfolio, just like an investment portfolio, you want a wide diversification of financial income, right? And you don't stick all of your eggs in one basket when you're investing. So too are you not going to stick all of your eggs in one energy source. That's a terrible idea. Just like your financial advisor is going to tell you, it's a terrible idea. So in 50 years, if we keep going on the unilateral path that we're going on, it's going to be a mess. You can't forget about the stuff that comes out the butt end of your smokestack. You can't forget about it because there's chemistry there. And we're seeing that in a very deleterious manner with ocean acidification, with climate change. Why do people keep scratching their heads when we're seeing more intense storms year after year? Now that's a very weak argument because that's weather. That's not climate. Climate, look at something over many, many millennia. But we have done that. We've taken ice cores from Greenland. We've taken ice cores from the Atlantic. We can see what happens when there are changes. Is the carbon dioxide anthropogenic, I guess is the word? It seems like it, because we can measure that. We can measure the isotopic content. We can measure the types of isotopes, the carbon-13 that's in there, or the carbon-14 that's in there, and all the other means of measuring, of isotopic measurement, that we can use to date these ice cores. And we can measure that, and we have measured it. So what are we going to look like in 50 years? I'm not sure.
Why do you think people are more skeptical of science in general and scientists in this day and age?
Because they unfortunately, at least here in the United States, there is a very large anti-intellectualist movement, and unfortunately it's couched in religion. You see it everywhere. Why do people go around peddling a young earth theory, which is stupid? Why do people go around peddling all of the non-science or pseudoscience that they think? It's because they have an agenda. Molten salt reactors are not a panacea. Molten salt reactors are not the holy grail of energy. They're not. There are very real challenges. So let's address those challenges. Because for me as a scientist, those challenges, solving problems are exactly what a scientist does. There's the Protactinium issue with a molten salt reactor. There's the uranium-232, 233 issue with a molten salt reactor. There is nevertheless a very small amount of plutonium-239 that ends up. Well, let's talk about those things. Let's figure out clever ways to solve those problems. And with some of the talent on this bus and some of the world-class scientists who are interested in these types of problems all around the country here in the United States, with whom I have spoken directly, face-to-face, or scientists in Canada, chemists in Germany, chemists in the Czech Republic, we're very interested. That's fun for us. So let's do it. Let's just do it. Let's make a concerted effort. I think the threat is very real. I think there's a very real threat to, as you said before, in 50 years, what is this planet going to look like? We're trying really hard. We're trying to do really good chemistry and really good physics, and we're trying to use the tools that we have here to try and make it better for my kids, for my grandkids. I will have grandkids in 50 years if I'm still alive. I hope I'm still alive, but if I'm dead, so be it. I hope I'm still alive. I hope I'm alive enough to see my grandkids. I'll be 93. And I hope I will have done my best to make this world a sustainable, better place.
Would you say you feel a personal responsibility?
Absolutely, I feel personal responsibility. Absolutely, without question. And if I may tend to be politically incorrect, I feel a responsibility because there are so many ignorant humans around me. And that's where I get very angry. Go open a high school chemistry book. Go open a high school physics book. Don't even worry about undergrad. Don't even worry about graduate school. All the answers are right there. The chemistry, by and large, hasn't changed one iota in the past 40, 50 years. Sure, we've gotten new techniques. Absolutely. Sure, we've discovered a lot more stuff. You know, the strong force, quantum chromodynamics, quantum electrodynamics. We've understood a lot more stuff. But by and large, the chemistry hasn't changed a bit. Go reread those books. It's not that hard. They don't use calculus. They don't use any advanced mathematics. It's right there.
So you think that ignorance related to nuclear power?
Ignorance related to science in general. Look at our members of Congress. There is a very real threat right now to our helium reserves. You actually had members of Congress saying 2 weeks ago in the New York Times, you actually had members of Congress saying, why do we still have helium reserves? The Army doesn't use blimps anymore. You actually had members of the United States Congress saying crap like that. Talk to any science teacher, even a high school science teacher, and they'll tell you helium has fabulous properties. Fabulous properties. Fabulous kinetic properties. Heat capacity properties. It's completely chemically inert. You can do lots of stuff with it. You can do lots of stuff with helium-4. You can do lots of stuff with helium-3. The United States Navy uses lots and lots and lots of helium gas for very, very good reasons. And none of them in blimps. So I have a big problem with members of Congress. Look at that clown from Georgia who actually was saying evolution is from the pit of hell. Are you out of your mind? You're a licensed physician. Stop prescribing antibiotics because they are a direct result of evolutionary theory. And not theory as the idiots are using the connotation of the word theory. Theory is model supported by evidence. Model supported by evidence. Gravity is a theory. Why? Because it's a model supported by evidence. Is it a law? No. We know the extreme situations where gravity fails, gravitational theory fails. Does an electron fall? No, it doesn't. Why? Because its mass is so small, it's no longer bound by gravity. Same thing with a neutron. Same thing with a proton. You have to get a fair amount of mass together before you start becoming susceptible to gravity. Does gravity nevertheless work really, really, really well? Yeah. Same thing with evolutionary theory, and you've got this United States senator saying this. Are you out of your mind? Stop prescribing antibiotics because they are as a direct result of evolutionary theory. And all the research that all the molecular biologists and all the biochemists have been doing for the past 40, 50, 60 years.
Paint me a picture of what the world could look like in 50 years if we did use MSR.
If we used molten salt reactors in a clever fashion and deployed them in strategic locations, we could fundamentally change our energy landscape. We could therefore fundamentally change our ecology and bring it back to where it should be. Bring it back more into equilibrium. I think that's what climate change is. It's a shift in equilibrium. You've gone from one system, and you have now perturbed that system and shifted it to now a new equilibrium. And that's not good. We now have, I think it was in the New York Times 3 weeks ago, we are now at 400 ppm of CO2 in our atmosphere. That's 0.04%. I know what carbon dioxide does. I know how and why it can retain heat. Talk to any chemist, and they'll tell you precisely why it can retain more heat than the nearby oxygen and nitrogen molecules that are in our atmosphere. Because it's not that difficult to understand. So when you know that fact, you need to start thinking about why we are seeing what we're seeing. You know, I'm not going to assign blame here. I don't care about who did it or what did it. We are still in our industrial revolution, but we have not been good stewards. We have been very, very, very myopic stewards. We have been, in many cases, sloppy. And we haven't thought about the cradle-to-grave trade-offs that have to be thought about and have to be attended to. In 50 years, we could drop our CO2 levels, maybe even back down to 200 parts per million. We might be able to build up the ice cap again. We might be able to. There's a lot of things that could happen. I'm not sure. You know, I'm not sure.
What kind of technologies would this inexpensive clean energy enable that we are using?
My God, the list is endless, but it would be politically, tricky. With a heat platform like a molten salt reactor, you can do any number of high temperature reactions. You could make dimethyl ether. You could make boatloads of dimethyl ether. Are there cleverer ways to maybe pull that off? There might be. There's a researcher actually out at Stony Brook University, the Advanced Energy Research and Technology Center out at Stony Brook, who's working on near room temperature ways of producing dimethyl ether. He may succeed. Awesome. Good for him that he's able to look at that. But there's all sorts of very, very interesting chemistry that we have actually never even been able to have the opportunity to look at, because we've never had a cheap energy platform, a cheap heat source platform like that, where we could play around at those temperatures. There's all sorts of I mean, dimethyl ether is a fabulous example. I personally like the idea of looking at lots of different isotopes that could be made at those temperatures. I'm sorry, at those neutron fluxes. You don't need the heat, but you need the neutron flux. I mean, the opportunities abound. I couldn't even tell you. There's so many possibilities. I wouldn't even want to predict. Wouldn't even want to. There's so many possibilities. The possibilities are endless. Off-world. Go off-world. You know, Kirk Sorensen's ideas about planting one of these suckers on the surface of Mars, or Max Zubrin with the Planetary Society, I think is the name of the group. Max Zubrin getting to Mars, you know, going to the moon, colonizing, doing science work in microgravity environments like that on the moon. You know, looking at the geochemistry of the surface of Mars with our hands right in the soil, human hands right in the soil, rather than doing it robotically. NASA and JPL have done a fabulous job of doing that. But my God, if we have an energy platform that's that cheap, and like in the paper that we wrote, and then in the talk that I gave, if we could have a space-based nuclear application, my God, we're going to Europa. We would be going to Io. We would be looking at those chemistries and those physics that are occurring on those moons of Jupiter. My God. With a heat source in microgravity, you could grow some of the most exotic crystals that simply can't be grown on this planet. I mean, seriously, like you can't grow certain crystals because of the gravitational field. But if you add 600 degrees Celsius and you're doing it in 1/5 the Earth's gravity, or if you're doing it in microgravity where there's near zero gravity on a space station, holy cow! Holy cow! And your energy source is with a 600 degrees Celsius energy platform like a molten salt reactor on a space station. You could literally go back and forth to Mars using planetary rocketry technology, because with an MSR on the surface of Mars, you can harvest all your oxygen that's already buried in the soil easily. You can use an inductive furnace, because you're making boatloads of electricity. You can make an inductive furnace to literally get all that oxygen off, liquefy it, and fly back and forth. No problem.
And have you breathe gas while you're there.
And you could even start terraforming. Let's terraform Mars. But we need an energy source in order to do it. We can terraform Mars with an energy source that intense.
And Kim was saying there was a gas molecule that we could use in lieu of nitrogen that's too heavy to be blown away by the solar winds, so you can rebuild an atmosphere on Mars. I forget what it is. It's an inert one that we can breathe. So it'd be, instead of nitrogen, oxygen, it'd be this thing plus oxygen and the solar wind, because Mars doesn't have a molten core, so it doesn't have a nitrogen.
Correct.
Field.
Yeah.
So you don't want the solar wind to blow away whatever atmosphere you create. And he was talking about a chemical.
There are many chemicals. There are many gases that are biologically inert.
A heavy gas.
Sulfur hexafluoride.
I think it's sulfur hexafluoride.
Sulfur hexafluoride is very, very heavy.
Instead of a nitrogen-oxygen atmosphere, you have a sulfur hexafluoride oxygen atmosphere. It wouldn't get blown away by the solar wind, and you can breathe it.
You could. Your voice will change, though. Okay. Yeah, everybody's voice. Actually, I would probably go lower because it's so much heavier. It would actually probably go lower.
We'll all sound like John Wayne.
Yeah. I don't know. I'd have to.
Macho dude settling the universe.
I'm not. I'd have to look that up. I'm not sure about that. Yeah, I'm not sure about that. But it would definitely change the frequency range of your voice. I'm a free market guy. I'm an entrepreneur. I love free market economics because it's how stuff moves forward. But I'm a realist because there are certain situations where free market economics just doesn't work.
Well, in a finite system, there are limits. You know, and that's
and you're not being a socialist or a communist by saying that.
No.
I love free market economics.
Yeah, but
I know when it doesn't work.
Yeah. Any system has its limitations, and my problem with free marketeers is they have that 500-year-old presumption that there's an infinite chessboard, you know,
no, there isn't.
And a bottomless trash can. It's just not true.
It's not true, and it wasn't true when Adam Smith wrote The Wealth of Nations.
But they didn't really know that then. I mean, really know
Adam Smith very well knew that.
He probably did, but the people that subscribed to his theories probably went, well, look at that great new world out there. How can you imagine running out of trees?
See,
well, here we are. You know.
I mean,
you get what I'm going for.
Yeah. I mean, I never struggled through the entire Wealth of Nations book, but I had to read pieces of it, and he very well knew that there was finite, limited resources.
He did.
Absolutely, he did. I mean, it's all
I understand he did, but I think a lot of people that ran with his theory or were inspired by what he wrought didn't think that through nearly as well as he did.
Yeah.
You know?
What do you guys think the role of government should be in advancing MSR?
Do exactly what they did in the 40s, 50s, and 60s, but just be motivated not by extrema like Cold Wars and you know, ideological, you know, browbeating.
Can we still do what we did in the 40s, 50s, and 60s?
In theory,
I am a skeptic. In the United States, I do not think that we can do that. I think the United States government is wholly incompetent at doing that anymore. And the reason is that we've lost our pragmatics. We've lost our go out and do it attitude. That does not exist in Congress, and it's ultimately Congress that decides where the money goes. Look at the superconducting super collider. Gone. We could have done some fabulous fundamental research. Gone.
Can you imagine Obama or Bush or Clinton, irrespective of party, but any modern president setting a goal of like going to the moon? You know, I don't see that vision coming out of. I don't see that vision coming out of the White House, irrespective of which party is controlling it, in the last 20, 30 years. More 20 years, more like 30, 40 years.
Yeah.
You know, that vision setting. And I think the goal of government, I think the government needs to create and maintain a level playing field in which commerce can occur. And part of that is building the infrastructure, and part of that is the intellectual infrastructure of basic science, you know, and the physical infrastructure like Eisenhower's, you know, St. Lawrence Seaway, the national highway system. And we're not having those big projects, and they're not like make work projects. This is like national infrastructure. There's 6,000 bridges that need to be rebuilt. That's infrastructure. Why build a bridge? So commerce can occur. Why do you want commerce can occur? So you have taxes to fund the damn government. I mean, you know, that's how the bridge gets paid for. And people are going, well, why should we spend all our tax money to fix a bridge? You know, so a truck can drive over it, so the company can make a profit and pay money on taxes. You know, that's how they get paid for. That's how Eisenhower calculated that the national highway system should be funded by the government because it would ultimately result in long-range revenue. And I don't think that you have that thought process even occurring anymore.
Right. Is this why molten salt reactors should be in the best interest of our government?
Absolutely.
Cheap abundant energy that isn't reliant on a foreign source.
Right, but you're not going to move that. Look, the national laboratory system, the 22 national laboratories here in the United States do some fabulous world-class research. Fabulous. The NSLS-2 is being built at Brookhaven. You've got some great research being done at Los Alamos, at Argonne, at the APS, the Advanced Photon Source. But when the projects are politically sensitive, like cheap energy, like a molten salt reactor, you're not going to get it done because there are too many entrenched, vested, well-paid interests. This isn't conspiracy theory. It's very obvious. You just go look it up. This isn't conspiracy theory. Like Mike was saying,
Radioactive water.
let us in. Let us in so we could do our thing. Let us in. There's enough room for us to play. And go make this thing.
Politicians are so dependent on money that they're obviously dependent on the people with the money.
Right.
And the people with the money is the fossil fuel industry that has $27 trillion in proven reserves.
Right.
You know, and nobody.
Or big nuclear.
They're not going to let anybody
big
tip
nuclear.
over the rice bowl.
Right. Yeah. You know,
big nuclear is with them.
Big nuclear is metal. You know, MOX metal. Solid oxide fuel.
There's no conspiracy necessary.
No, there's not necessary.
It sounds like a conspiracy theory, but there's no conspiracy necessary. If you have an economic system that compels people to maximize profit and eliminate the competition, people will appear as if they are acting in concert, in other words, conspiring, breathing the same air, conspire. That's what it is. Spire, breathe, con with, right? And so it looks like a conspiracy, and it's not a conspiracy.
It's not.
They're generally herding in the same direction.
Yeah.
They're wildebeest going toward the water.
How can we change this then?
You can't. Write checks.
Take money out
Write
of
checks.
politics or put money into politics.
Yeah. You only have two choices.
Yeah.
Either take money out of politics, which the Dodd-Frank bill failed miserably. It failed utterly.
And then the Citizens United, oh my God, that just opened up the door.
Right, it made it even worse.
And so there's alpha, beta, gamma, neutron, and proton radiation. Some of these are used to kill cancers, for instance, which then exposes the reality that radiation can be good, because if you use it correctly, you can kill the bad cells that you don't want in a living thing, and you can protect the good cells that you do want. And so people can understand, when they realize the medical application of radiation, that there are significant reasons to understand that there is in fact a minimum level of radiation that is no longer harmful. Once you get below a certain level of radiation, there is no reasonable effect on a living organism. The reason for that is because radiation was always present on Earth for all its history, and higher in the past, because radiation actually means that some material is going away. It's decaying away and giving off energy, giving off particles as it decays away to a more stable element. So the radioactive elements are disappearing. Unlike dangerous chemicals, which typically don't disappear, like PCBs and so forth, radioactivity means something's going away. If things have been going away for the 5 billion years that Earth existed, that means that there were many more things back then that were radioactive, and so the radioactivity in the environment was much higher. So nature naturally must have had to deal with radiation for billions of years, and it has. And what happens is that there are cellular repair mechanisms that repair the damage caused by radiation, or the foods we eat, that kind of thing, or the chemicals we ingest or breathe. The 1946 statements by Hermann Muller, who got the Nobel Prize for his radiation and genetics work, but made a misstatement that resulted in a standard that since then has been unreal. So there is in fact a level of about on the sievert scale of about 100 to 200 millisieverts. The United Nations currently admits that there's no way to determine if there is any damage at all, sensible damage to a living organism by 100 millisievert worth of radiation. Now, what does that mean? That means that that's the kind of radiation, that sort of radiation from 100 to 200 millisieverts is what a Fukushima worker got when he's trying to go into the plant and do cleanup work. If that person, and none of those people have experienced any problems.
The fact that we used to build entire reactors in the amount of time it takes them to string together a couple pieces of plumbing. Have we lost the ability to fabricate stuff to the extent that we can't even build a freaking high temperature pump in this country anymore? Yeah, like we were there, and when we were there, it was just like a bunch of pipes and crap laying on the ground. and they had some like super high temp insulation, you know, sitting in that big hot box. You saw that.
So you're talking about 2011 then?
Yes, that would be 2011, January of 2011. That's when we were down to give a presentation to Oak Ridge. Jim was speaking about rare earths and the critical nature of rare earths and stuff, and we got a tour of that salt loop, and so my opinion is, it's like, if you're going to spend that much money, you better have a freaking salt loop running, dude. Man, I could, from this bus, from my phone, order all the parts I would need for a basic salt loop from Columbia Pipe and Supply in Chicago here. Even some high temperature, we got enough industry in Chicago that we still have guys that make the super high temperature pumps that pump lead and aluminum for aluminum injection molding. And that's enough to get, you don't need to get up to 700-800. You know, I could make a salt loop out of 3/16 stainless plumbing and a crucible and a big pot and some valve. You don't even need the valves. And maybe a real MSR wouldn't even have valves. Point is, I could build a salt loop for under $100,000 probably with a rebuilt, you know, aluminum injection mold pump. And it's like, the point is, get to it, fuckers. Get some Flynac or Flybe or whatever, melt that shit down and start studying its properties. I mean, that's the whole point of a salt loop. If you're not going to make it radioactive, then what are you doing? Oh, if you have a 6-inch pipe and you make it turn this diameter without heat tape in the corner, you're going to get a freezing place, you know. I mean, those sorts of basic knowledge, one, they're being lost because, you know, the library of knowledge that is guys like Dick Engel and Yuri Gott are going to be dead someday, and all that knowledge that's stuck in their head about what it was like to actually run a full-size molten salt reactor is gone. You know, it's like what they say when a professor dies, a library is burned to the ground. You know, we only have so much knowledge. The O&L, the amount of records they kept, just fabulous. I mean, it's almost unbelievable the level of detail that they kept. Of course, now the Chinese downloaded it, yeah, so they got a nice leg up on that. You know, there is one more set of documents about the MSRE that have never been scanned that I personally, I always tell people, you know, they're like, why don't you do this? Why don't you do that? I'm like, I have the 500 item punch list of things that people want me to do, and like the 4 or 5 things that, you know, me and Vince are able to actually do. You know, so one of those 500 things that I would love to do would be to get another $10,000 and scan those next documents in, but in some sort of like bizarre archaic format, only readable by Commodore 64s, right. So that like only we could have them, you know, and I'm gonna record them to like Sony Betamax tapes, deck tape, and laser disc platters, you know. and the only way you can get to them is you need an acoustical coupler and about a week to download each image. So that literally the night before the little mini conference symposium thing, you know, texts started coming in, emails. It was like, holy crap, did you see this? And the CAS, the Chinese Academy of Sciences, and I think it was the CNCC, the sort of the Chinese National Corporation for, you know, building nuclear power plants. I think it's like Chinese Nuclear Corporation or something like that. They released their press release, you know, with those very ominous words that we've come to use, that, you know, said, you know, we will pursue thorium molten salt reactor, you know, not picky eater, but, you know, the ominous words are at the bottom of it where it says, we endeavor to control all intellectual property involving this type of reactor, and we will commercialize it and sell it to the world. And so, you know, that's the sort of thing that will raise Jim Kennedy and me's hackles, where we go, hey, you know, that right there is what we're talking about, folks. If they get the, you know, all that knowledge that Dick Engel and Yuri Gott and all the rest have in their head, that's what they're trying to do right now, is build up that cadre of super informed engineers, which we don't have in this country anymore. People really working every day, day to day in molten salts. I mean, they're ingenious. They're like, this will take us 10 to 15 years to develop this, because they understand that they can't just rush and build a reactor. If they want to make an industry, they have to have a supply chain of human capital. The reason it's so critical to get this into our universities is that if we want this to be an industry, we can't just build, you know, a monolith of a reactor sitting in a parking lot somewhere. There have to be thousands and thousands of engineers that build these and maintain them and create the salts and reprocess the fuel, and that doesn't exist at all anywhere in the West. I mean, the 10 guys that know how to fabricate fly, I mean, there's like 2 at Ornell and maybe 1 at Materion. You know, I mean, China is building a supply chain in order to manufacture and distribute molten salt reactors, and we are not. And that's my desperate little cry in the wind, like a little sparrow in a hurricane going, please, can't we start teaching this? And I swear to God, there will be jobs for you at the end of the mill, you know. I always tell them, I'm like, hey, learn about it, and you can always apply it to something else. Why not be a radiochemist? I mean, the rarest of all birds is radiochemistry. We used to graduate hundreds of radiochemists a year back in the 60s. 2 years ago, we had the head of the American Radiochemistry Society. You know how many PhD radiochemists we graduated? 1 in the entire country. Because how do you convince a kid this is the hardest of hard things to learn? Radiochemistry is studying, you know, not only radioactive materials, but the isotopes and how they so you're talking about materials that are changing state while they react. I mean, it's like 3-dimensional. You think chemistry is hard or chemical engineering is hard? You know, make it 3 times harder, because it's like 3-dimensional chess of chemistry. And so kids these days, what, I'm going to go into that and make what any normal engineer or PhD does when I could like design the next Angry Birds? No, you're crazy. I'm going to use all my brain power to learn how to play the stock market and be a quant. It's incredibly disheartening, you know, that we don't keep up this supply chain. It's a human supply chain. You know, there's material supply chains and stuff, but you need the human beings to get in on that. Oh, shit, is it Blues Fest? Is that why we're so backed up?
Oh, is that what it is?
It could be. I mean, finding investors that are willing to get a return in like, oh, 10, 15 or never, you know. But I do it because I do believe there is some aspect of this that's going to work out. I mean, my dream is obviously, you know, bigger, but my core dream at this point, if all I could do is get the thorium bank done, if all I could do is get the thorium bank to become a reality, to open up the possibility of a domestic rare earth, then I will have done a great good deed for this country and the West, and I could like hang up my hat at that point and be like, Tag, it's your turn to try and get the rest of this crap done. You know, you guys can try and, you know, you guys can try and get power out of this stuff, but I left you a great big pile of it inside this box, you know. So when the time comes for you to make energy from thorium, you know where to find it. I left it in this big box for you. But in the meantime, you know, Canada, Germany, the United States, Japan, everyone can come and, you know, enjoy the fruits of a second source of rare earths in the world, you know, and that would be a huge thing for the West, and it would be a great thing for my country, the United States. The people who want rare earths from a country that won't steal your intellectual property, and that is a lot of companies, you know, they are willing to pay what amounts to a modest fee to store the thorium to get that pain in the ass out of there. But to us, in this bus, that modest fee could amount to a very large amount of money that far exceeds what it costs to safely store thorium. So what do you do with that money? Well, The legislation says it right there. Come up with uses, including energy, for the thorium. And so we could fund, you know, a molten salt reactor. You know, Magdi Ragheb said he could build a hell of a molten salt loop for under $3 million. And he said he'd do it in like I said, you know, basically ordering off the shelf stuff in about, you know, 6 months. We're not asking for our national lab to do miracles. We're asking them to basically replicate something they did, you know, in 1952 probably. You know, my heroes are the guys who worked on the aqueous reactor. You know, those guys, I thought that was a panic. They're like, it burnt another hole in the reactor. They'd like wipe it off and they'd solder a patch onto it and run it. Today, the action item list for the NRC, oh, they'd be sequestered. They'd pour a concrete sarcophagus around it, you know. But back then, you know, like some radioactive water spilling out on the floor, and they're like, oh, God damn it. You know, they'd like dry it off and solder a new patch on it. And they did that like 7 times. You know the Chinese are doing that. Not bad leak, experiment almost over, keep going. You know, I mean, but that's the sort of attitude we used to have. That's why we got stuff done so quickly.